Welcome to Earthly Teachings, where learning is clear and powerful. Today we are working on Mathematics N6. Let's learn together. We'll be focusing on calculating volume, specifically the volume of solids of revolution. By the end of this video, you will be able to define and visualize solids of revolution, understand the disk and shell methods, and apply their formulas to calculate volumes. Our main goals are to define solids of revolution, understand the disk and shell methods, and apply these methods to calculate volume. You might remember the disk method from N5. In this unit, we're going to dive deeper, using it to solve more complex problems and introduce a new, powerful tool, the shell method. First, let's establish some foundational concepts. What is a solid of revolution? Imagine you have a two-dimensional shape on a graph. If you spin this area around a line, it sweeps out a three-dimensional solid. This 3D figure is what we call a solid of revolution. The space it occupies is called the volume generated. The volume generated is the space occupied by a solid of revolution. The line you rotate the area around is crucial. It's called the axis of rotation. The axis of rotation is the straight line about which an enclosed area is rotated. Let's see this in action with a simple example. Consider an isosceles triangle with its axis of symmetry on the x-axis. If we take this triangle and rotate it about the x-axis, the axis of rotation, what shape do you think we'll create? The space occupied by the triangle as it spins creates a right circular cone. It's important to visualize these solids. The cone is a classic example of a solid of revolution. Similarly, rotating a circle or semicircle about its diameter creates a sphere, and rotating an ellipse creates an ellipsoid. Now, let's talk about a very important property that can simplify our calculations. Look at our isosceles triangle example again. If we rotate only the top half of the triangle about the x-axis, the solid created is still a cone. In fact, it creates the exact same solid as rotating the entire triangle. This brings us to a key rule. If the area you're rotating is symmetrical about the axis of rotation, you only need to consider 1/2 of that area to calculate the total volume. Then you can rotate just that half to get your result. This can save you from dealing with more complex limits of integration. Now, how do we actually calculate this volume? We use a technique you may have seen before in integration. The strategy is to slice the solid into very thin pieces, either thin disks or thin cylindrical shells. We find the volume of one of these representative elements and then use a definite integral to sum up the volumes of all the infinitely many, infinitesimally thin pieces. This summation gives us the total volume of the solid. Based on how we slice the solid, we use one of two methods, the disk method or the shell method. Let's look at the disk method first. The first method we'll discuss is the disk method. The defining characteristic of the disk method is that the thin strip we draw on our 2D area is always perpendicular, or at a 90-degree angle, to the axis of rotation. Remember this rule: disk method is perpendicular strip. Let's revisit our triangle rotating about the x-axis to form a cone. Using the disk method, we'll draw a thin vertical rectangular strip. This vertical strip is perpendicular to our horizontal axis of rotation, the x-axis. It has a tiny width, dx, and its height is the y value of the function. Now imagine spinning just this single strip around the x-axis. What shape does it trace out? It forms a thin, flat disk, which is essentially a very short cylinder. The volume of any cylinder is given by the formula PR²h. In our case, the radius of the disk, r, is the height of our strip, which is y. The thickness or height of our cylinder, h, is the width of our strip, dex. So the volume of this single disk is πy² times dx. To find the total volume of the cone, we need to add up the volumes of all the infinite disks from x equals 0 to x equal a. We do this by taking the definite integral of our disk volume formula. As dx becomes infinitely small, it becomes dx. The total volume is the integral from 0 to a of πy² d. That was for an area between a curve and the x-axis. What if the area is between two curves? This leads to a concept known as the washer method. It's not a new method, but an extension of the disk method. We use it when the solid of revolution is hollow. Imagine you're rotating an area that has a hole in it. This will create a solid of revolution that is hollow, like a washer. The formula is very intuitive. We find the volume of the larger outer solid and subtract the volume of the smaller inner solid. If y1 is the outer radius and y2 is the inner radius, the volume of a single washer is pi times the difference of their squares, all times dx. The total volume is the integral of this expression. A key thing to remember is the order of subtraction. It's always the outer radius squared minus the inner radius squared, not the other way around. If you get it wrong, you'll end up with a negative volume, which is physically impossible. Volume is always positive. Now let's look at the disk method formulas in summary. The logic is the same if we rotate about the y-axis, but the variables change. Remember, the strip is always perpendicular to the axis of rotation. So, for rotation about the y-axis, the strip must be horizontal with thickness di and length x. Here you can see the complete set of formulas for the disk method. Notice the pattern. If you integrate with respect to x, everything inside the integral must be in terms of x. If you integrate with respect to y, everything must be in terms of y. This often means rearranging your function. Now let's move on to the second major technique, the shell method. The shell method uses a completely different type of slicing. Instead of disks or washers, it uses thin, hollow cylindrical shells. The key distinction here is that the strip we draw on the 2D area is always parallel to the axis of rotation. This is the opposite of the disk method. Let's use our triangle example again, but this time for rotation about the x-axis, we'll draw a horizontal strip. This horizontal strip with width d and length x is parallel to the x-axis. When we rotate it, it forms a thin cylindrical shell, like a tin can with the top and bottom removed. The solid created is a hollow cylindrical shell. To find the volume of this shell, there's a clever trick. Imagine cutting it and unrolling it into a flat, thin rectangular sheet. If you cut the shell lengthwise, it opens up into a rectangle. The length of this rectangle is the circumference of the shell, which is 2 pi r. The width is the height of the shell, which is our strip's length, x. The thickness is our strip's width, d. The volume of a rectangular prism is length times width times height. So, the volume of our shell is 2 pi y, the radius, times x, the height of the strip, times d, the thickness. This formula, 2 pi rht, where r is radius, h is height, and t is thickness, is the core of the shell method. To find the total volume of the solid, we integrate this shell volume formula over the appropriate range for y. The total volume is the integral of 2 pi x di. Just like with the disk method, we can adapt the shell method for rotation about the y-axis and for areas between two curves. Here you can see the full summary of the shell method formulas. Notice the variables are reversed compared to the disk method. For x-axis rotation, we integrate with respect to y. For y-axis rotation, we integrate with respect to x. This is because the strip is parallel to the axis. It's also worth noting how the area between two curves works. Instead of squaring the difference of radii, we simply multiply the circumference by the difference in the strip's length. So for rotation about the x-axis, the volume is 2 pi times the integral of y times the difference in x values, dA. This gives us a complete toolbox. But how do we choose the right tool for the job? That's the next critical step. Let's formalize the procedure for solving these volume problems. There are two main steps. Step 1 is to draw a clear picture. Sketch the graphs of the functions involved to identify the specific enclosed area you need to rotate. Don't skip this step. A good diagram is a roadmap to the solution. It helps you find the limits of integration and define the radius or height of your strip correctly. Step 2 is to choose your method. This means selecting a representative strip. Once you've chosen your strip, apply the corresponding formula, either disk or shell, to find the volume. How do you choose? It's all about the strip. If you want to use the disk method, the strip must be perpendicular to the axis of rotation. If you want to use the shell method, it must be parallel. Sometimes, one choice leads to a much easier integral than the other. Other times, one method is simply not possible. This choice is the most important decision you'll make in the problem. Before we dive into examples, there's one more important concept. You might see a formula like this. The formula for a strip between two curves, like v sub x equals pi times the integral of y1 squared minus y2 squared dx, is actually the more general form. The simpler formula for a single curve, v sub x equals pi times the integral of y squared dx, is a special case. You can think of the x-axis y equals 0 as the second inner curve. When you plug y sub 2 equals 0 into the general formula, it simplifies directly to the single curve formula. So you can think of the single curve case as always being between the main curve and the axis itself. It's the same logic for all four formulas. This means the two curve formulas are always valid, even for one curve problems. The shell method formula can seem a little less intuitive than the disk method. Let's take a moment to see where the 2 pi rht, or in our case 2 pi y x delta y, comes from. Let's consider a hollow cylinder. It has an inner radius, an outer radius, and a height h. Let's label the inner radius r1, the outer radius r1 plus a small change delta r, and the thickness of the wall delta r. First, let's find the volume of this hollow cylinder using what we already know. It's the volume of the large cylinder minus the volume of the small cylinder. This gives us pH times the difference of the squares of the radii. We can use the difference of squares factorization. A squared minus b squared equals a plus b times a minus b. This simplifies our expression. Now let's introduce the concept of an average radius. The average radius r is the average of the inner and outer radii. If we solve this equation for 2r, we find that 2r is equal to 2r1 plus delta r. We can substitute this expression into our volume formula. Look at what we get. V equals pi h times 2r times delta r. Rearranging this, we get V equals 2 pi rh delta r. This is the exact form of our shell method formula. The average radius r corresponds to the distance y from the axis, the height h corresponds to the length x of our strip, and delta r is the thickness delta y. All right, let's put these methods to the test with our first full example. We need to calculate the volume when the area enclosed by the function y equals 2 sine 2x, and the x-axis in the first quadrant is rotated about the x-axis. Step 1. Sketch the area. The first quadrant means x is from 0 to pi over 2. The scene function starts at 0, goes up, and comes back down. The 2 in front stretches it vertically, and the 2 in the argument shrinks it horizontally. So it looks like a single bump from x equals 0 to x equals pi over 2. This is our shaded region. Step 2. Choose a method. We are rotating about the x-axis. The disk method uses a perpendicular strip, which in this case is a vertical strip. The shell method uses a parallel strip, which is a horizontal strip. If we use a vertical strip, disk method, its height is y, which is 2 sine 2x. That looks easy to integrate. If we use a horizontal strip, shell method, we'd need to express x in terms of y, which would involve an arcsine function, a more complex integral. So the disk method is the better choice. Because our strip is perpendicular to the x-axis, we use the disk method formula, pi times the integral of y squared dx. Now let's execute our plan from example 5.6. We've chosen the disk method. The limits of integration, our a and b, are the boundaries of our area along the x-axis, which are 0 and pi over 2. The function is y equals 2 sine 2x. So we substitute our function and limits into the formula. Remember to square the entire function, 2 sine 2 squared. Squaring gives us 4 sine squared of 2x. We can pull the 4 out of the integral. Now we need to integrate sine squared of 2x. A common mistake here is to think you can just integrate sine of 2x and square the result. You can't. You need to use a trigonometric identity. The double angle identity for cosine is your best friend here. We can rewrite cosine of 2a as 1 minus 2 sine squared of a. If we replace a with 2x, we get cosine of 4x equals 1 minus 2 sine squared of 2x. Solving for sine squared of 2x, we get sine squared of 2x is equal to 1/2 minus 1/2 cosine of 4x. This is a much easier expression to integrate. Substituting this back into our integral, we can pull the 1/2 out, leaving us with 2 pi times the integral of 1 minus cosine of 4x d. Integrating term by term, the integral of 1 is x, and the integral of cosine of 4x is sine of 4x over 4. Now we evaluate this expression from our upper limit, pi over 2, to our lower limit, 0. Plugging in the limits, we get 2 pi times pi over 2 minus sine of 2 pi over 4 minus 0 minus sine of 0 over 4. Sine of 2 pi is 0, and sine of 0 is 0. So the whole expression simplifies to 2 pi times pi over 2. This gives us a final answer of pi squared cubic units. The prompt also asks for a numerical value, so pi squared is approximately 9.87 neurocubic units. So we successfully used the disk method. The key was recognizing that a vertical strip was perpendicular to the x-axis, and then using a trig identity to solve the integral. Now let's tackle the second part of example 5.6. This time, we're rotating the same area, y equals 2 sine 2x, but about the y-axis. Let's think about our strip. For rotation about the y-axis, if we were to use the disk method, the strip would have to be horizontal. We already determined that this would lead to a difficult integral involving arcsine. Instead, let's use the shell method. The shell method requires a strip parallel to the axis of rotation. A vertical strip, like the one we used for the disk method, is parallel to the y-axis. This should work much better. We use the shell method formula, v sub y equals 2 pi times the integral of xy dx. Substituting y equals 2 sine 2x and our limits of integration 0 to pi over 2, we get 2 pi times the integral of x times 2 sine 2x dx. This simplifies to 4 pi times the integral of x sine 2x dx. This is an integral of a product of two functions, so we need to use integration by parts. Let's perform the integration by parts for example 5.6, part 2. We need to integrate 4 pi times the integral of x sine 2x dx. The formula for integration by parts is the integral of u dv equals uv minus the integral of v du. We use the mnemonic LIATE to choose our ul for log, I for inverse trig, A for algebraic, T for trig, E for exponential. In our integral, we have an algebraic term, x, and a trigonometric term, sine 2x. According to LIATE, A comes before T, so we choose u equals x. This means dv is sine 2x dx. Now we find du by differentiating u and v by integrating dv. Du is 1 dx, and v is the integral of sine 2x, which is negative cosine 2x over 2. Now we apply the formula. Our volume is 4 pi times the quantity u times v minus the integral of v times du. We can bring the negative 1/2 out of the integral. The integral of cosine 2x is sine 2x over 2. So now we have the fully integrated expression, 4 pi times x cosine 2x over 2 plus sine 2x over 4. Before evaluating, we can simplify this expression a bit by distributing the 4 pi. This gives us 2 pi times 2x cosine 2x plus sine 2x. Let's evaluate this from 0 to pi over 2. We plug in pi over 2 for x, then subtract the result of plugging in 0 for x. The sine terms both become sine of pi, which is 0. The cosine of pi is 1, and cosine of 0 is 1. The result simplifies to 2 pi times pi. And once again, we get pi squared cubic units, or approximately 9.870 units cubed. In this specific and rare case, rotating about the x-axis gave the same volume as rotating about the y-axis. Let's move on to our next example. This problem asks for the volume when the area bounded by y equals secant of x and the x-axis, from x equals 0 to x equals pi over 4, is rotated about the x-axis. Step 1. Sketch the graph. The secant function is the reciprocal of cosine. Cosine starts at 1 and decreases to 0 at pi over 2. So secant starts at 1 and increases as x approaches pi over 2. The area we are interested in is this region under the secant curve from 0 to pi over 4. Step 2. Choose a method. We are rotating about the x-axis. A vertical strip which is perpendicular to the x-axis would be easy to set up. A horizontal strip would involve an inverse secant function and be much harder. The disk method is the clear winner here. Using the disk method, the formula is pi times the integral of y squared dx. Our function is secant of x, and our limits are 0 and pi over 4. Let's solve example 5. We have the integral pi times the integral from 0 to pi over 4 of secant squared x dx. Fortunately, secant squared x has a very straightforward integral. The integral of secant squared x is simply tangent of x. This is one of those basic derivatives you should have memorized. The derivative of tangent x is secant squared x. So our volume becomes pi times the expression tangent of x, evaluated from 0 to pi over 4. Plugging in the limits, we get tangent of pi over 4 minus tangent of 0. We know that pi over 4 is 45 degrees, tangent of 55 degrees is 1, and the tangent of 0 is 0. So the volume is pi times 1 minus 0. This gives us a final volume of pi cubic units. Numerically, that's about 3.142 cubic units. An important exam tip. When you have trigonometric functions with pi in them, like pi over 4, your calculator must be in radian mode. Using degree mode will give you the wrong answer. Our next example introduces an area between two curves. This is where the washer and shell methods really shine. The problem asks for the volume when the area bounded by the curves y equals x squared plus 1 and y equals 9 minus x squared is rotated about both the x and y axes. Step 1. Sketch the graphs and find the points of intersection. The first curve, y equals x squared plus 1, is a parabola opening upwards with its vertex at 1. The second curve, y equals 9 minus x squared, is a parabola opening downwards with its vertex at 9. To find where they intersect, we set their y values equal. Solving x squared plus 1 equals 9 minus x squared. We get 2x squared equals 8, or x squared equals 4. This means x equals positive or negative 2. Plugging x equals 2 into either equation gives y equals 5. The intersections are at 2, 5, and 2, 5. So here is our sketch. The upward parabola is the inner curve, and the downward parabola is the outer curve. Let's find the volume of revolution about the x-axis for example 5.8. We're rotating this shaded area about the horizontal x-axis. Since we are rotating about the x-axis, the disk method requires a perpendicular vertical strip. The shell method requires a parallel horizontal strip. If we use a horizontal strip for the shell method, we would need to solve both equations for x in terms of y, getting x equals plus or minus the square root of y minus 1, and x equals plus or minus the square root of 9 minus y. Dealing with square roots in an integral is often challenging. Therefore, the disk method with a vertical strip is the better choice. We can clearly see which function is on top and which is on the bottom. The strip is perpendicular to the x-axis. So we use the washer method formula, p times the integral of the outer radius squared minus the inner radius squared, all with respect to x. In our region from x equals 2 to 2, the function y equals 9 minus x squared is the upper function, the outer radius. The function y equals x squared plus 1 is the lower function, the inner radius. The limits are the x-coordinates of our intersections on 2 and 2. Notice the area is symmetrical about the y-axis. The function is even. This means we can integrate from 0 to 2 and multiply the result by 2 to get the total volume. Integrating from 0 to 2 and multiplying by 2 is a great way to avoid dealing with negative limits and can simplify the algebra. Now let's complete the integration for example 5.8, part 1. We need to expand the terms inside the integral. We'll expand the first term, 9 minus x squared squared, and then subtract the expanded second term, x squared plus 1 squared. Distributing the negative sign and combining like terms, the x to the fourth terms cancel out, leaving us with 80 minus 20x squared. Alternatively, you could notice that the expression is a difference of two squares and factor it, which can sometimes be simpler, but this expansion method is always reliable. Now we can integrate. The integral of 80 is 80x, and the integral of negative 20x squared is negative 20p satas cubed over 3. We evaluate this expression from our upper limit 2 to our lower limit 0. Plugging in 2, we get 2 pi times the quantity 80 times 2 minus 20 thirds times 8. The lower limit gives 0. We combine the fractions. 160 is 480 over 3. 480 minus 160 is 320, so we have 2 pi times 320 over 3. This simplifies to 640 pi over 3 cubic units. Numerically, this is approximately 670.206 units cubed. Now let's find the volume of revolution about the y-axis for example 5.8. This time, we're rotating the same shaded area about the vertical y-axis. Since we are rotating about the y-axis, the disk method would use a horizontal strip, which we've already said leads to square roots and is difficult. The shell method, however, uses a parallel strip, which in this case is a vertical strip. This is the easier choice, so we'll use the shell method. The formula is 2 pi times the integral of x times the height of the strip. The height of our vertical strip is the top function minus the bottom function. This gives us 9 minus x squared minus the quantity x squared plus 1. This simplifies to 8 minus 2x squared. Just as before, the region is symmetrical about the axis of rotation, the y-axis. So we can integrate from 0 to 2 and multiply by 2. Substituting the height and limits into our formula, we get 4 pi times the integral from 0 to 2 of x times the quantity 8 minus 2x squared dx. We can distribute the x to make integration easier, giving us 4 pi times the integral of 8x minus 2x cubed dx. Integrating term by term, we get 4 pi times the expression 4x squared minus 1/2 x to the fourth. Evaluating this from 0 to 2, we get 4 pi times the quantity 4 times 2 squared minus 1/2 times 2 to the fourth. The lower limit gives 0. This simplifies to 4 pa times 8, which is 32 pi cubic units. Numerically, this is approximately 100.531 units cubed. As you can see, the volume of revolution around the y-axis is very different from the volume of revolution around the x-axis for this shape. Let's work through our final example, which involves a volume bounded by 4 different elements. We need to find the volume when the area bounded by the curve y equals x cubed plus a. The x-axis, the y-axis, and the vertical line x equals 1 is rotated about both the x and y-axes. Step 1. Sketch the area. The function y equals x cubed plus 8 crosses the y-axis at y equals 8. From x equals 0 to x equals 1, the curve rises. The area is bounded by this curve at the top, the x-axis at the bottom, the y-axis on the left, and the line x equals 1 on the right. This trapezoid-like shape is our region of interest. Let's find the volume of revolution about the x-axis for example 5.9. We are rotating this region about the horizontal x-axis. If we were to use the shell method with a horizontal strip, we would need to solve y equals x cubed plus 8 for x, getting x equals the cube root of y minus 8. A cube root in an integral is something we want to avoid if possible. Therefore, the disk method with a vertical strip is the simpler choice. This strip is perpendicular to the x-axis, so we use the disk method. Since the lower boundary is the x-axis, y equals 0, we can use the simpler formula v sub x equals pi times the integral of y squared dx. Our function is x cubed plus 8, and our limits are 0 to 1. We plug these into the formula, squaring the function. Now we expand the term. X cubed plus 8 squared is x to the 6th plus 16x cubed plus 64. Now this is a polynomial that is easy to integrate. Integrating term by term, we get pi times the expression x to the 7th over 7 plus 16x to the 4th over 4 plus 64. Simplifying, we get x to the 7th over 7 plus 4x to the 4th plus 64x. Now we evaluate this from 0 to 1. Plugging in 1 gives pi times 17 plus 4 plus 64. The lower limit of 0 makes all terms 0. This simplifies to pi times 68 and 1/7, which is 477 pi over 7 cubic units. Numerically, this is approximately 214.077 units cubed. Finally, let's find the volume of revolution about the y-axis for example 5.9. We are rotating this region about the vertical y-axis. As we discussed, Using the disk method would require integrating with respect to y, which means dealing with a cube root. The shell method, however, uses a vertical strip, which is parallel to the y-axis and involves integrating with respect to x. This is the easier choice. So we use the shell method formula. 2 pi times the integral of x times the height of the strip, dx. Here, the upper curve is y equals x cubed plus 8, and the lower curve is the x-axis, which is y equals 0. The limits of integration are the x boundaries of our region, 0 and 1. Substituting these into the formula gives 2 pi times the integral from 0 to 1 of x times the quantity x cubed plus 8 dx. Distribute the x, and we have a simple polynomial to integrate, x to the 4th plus 8x. Integrating term by term, we get 2 pi times the expression x to the 5th over 5 plus 8x squared over 2. Simplifying, this is 2 pi times x to the 5th over 5 plus 4x squared. Now we evaluate from 0 to 1. Plugging in 1 gives 2 pi times 1, 5 plus 4. The lower limit 0 makes both terms 0. We can write 4 as 20 over 5. So we have 2 pi times 21 over 5, which is 42 pi over 5 cubic units. Numerically, this is approximately 26.389 units cubed. Let's quickly review the strategies we've learned. The most important step is choosing the right method, and that depends on the direction of your representative strip. Remember the key rule. For the disk method, the strip is perpendicular to the axis of rotation. For the shell method, it's parallel. Don't forget that if the area is symmetrical about the axis, you can often simplify the problem by integrating over half the interval and doubling the result. We've covered the fundamentals of finding volumes of revolution using both the disk and shell methods for rotations about the x and y axes. This is a crucial topic in N6 mathematics. Thank you for watching. Like, subscribe, and continue learning with Earthly Teachings.